Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 25. I am Joseph Darnell, and I am joined by my good friend, Dr. Robert Carter. Hello, Rob.
Hello, Joe. Did you say 25?
Yes, we're halfway to 50.
That's like a quarter way to 100.
Yes, they call this not the silver edition. This is the bronze edition.
Okay, I'll take that.
I like that name.
I will tell you that I have been really enjoying these discussions. And this is one of my highlights of my week, the time I get to sit down with Joe and just ramble on about random fun stuff.
They continue to get just better and better. And I have found a few more listeners lately. Some of my new friends up in Tennessee. Hello, guys. If you're listening to this, let me know how you like it. I think we just continue to find more people, more listeners that do enjoy this sort of thing, but they don't know that it's out there.
Yeah, we got to find them.
I heard from a guy on Twitter this week who gave me a thumbs up on it, checking it out. In general, it is looking good for the future of Equinox. What I love about the show is, as any of our listeners already recognize, we can talk about so many different kinds of science subjects, for one, because of your basic knowledge and also what you can research. Science covers just so much, and we haven't tapped it all.
Oh, not even close. Even today's topic, I mean, we're just scratching the surface on some fascinating things, but that's just what you have to do.
Yeah. By the way, I wanted to give a huge bit of gratitude to my wife, who has been our editor now for many, many episodes.
She's doing a great job.
When I started the show, thank you. I agree. When we started, I had the time to do the post-production. And then I kind of got tired of it. And she said that she could and wanted to learn. So I sat down with her in front of the computer. In no time at all, she picked it up. Little by little, the show is also getting changes. It's a work in progress. So we've been lately tinkering with things like, if you're an audio engineer and you're listening to this, I know about things like noise gates and compressors, but I sometimes forget how I want to use them. And then I remembered again, and I've been explaining those things to my wife, and I think the audio is getting a lot better. So, which, by the way, if you are an audiophile, you might notice that I sound much better right now because I have my microphone positioned much better to my face. I did a whole bunch of recordings with my microphone in different places around me, and then I listened to them on earbuds, the car stereo, my computer, and my headphones, and I found the spot I liked most.
Cool.
And I'm sticking to this now.
Cool. Yeah, I've been very frustrated with my own podcast where I get everything edited just right, and I'll listen to it in the car, and all I hear is lip smacking. It's like, oh no.
It is so difficult to figure out how to limit all the noisy crackles that seem to get enhanced sometimes with certain kinds of audio filters. It's just painful to listen to.
Yes. I gave a church talk once, and I could not get the microphone away from the... And I heard it, and it was so loud. And I'm like, this is awful, because all I heard was smack, smack, smack for like an hour. I was trying to bend the little thing away from my mouth, would spring right back again. It's like, I looked at the sound booth, I'm like, giving them like the subtle nod, wink, wink, hey, this is awful, fix it sort of thing. And they couldn't do anything. So, oh well.
I just learned about how to filter out plosives. If you know what a plosive is, it's when you make a p, or a b sound, and it hits the microphone harshly.
How do you filter it out?
There's a filter for that. I can send it to you in Adobe Audition. It takes it right out of there. How you doing, Rob?
I'm doing very well.
It's been a busy week.
Yeah.
I've actually been catching up on a little bit more downtime, be able to focus and create some more margin in my week lately. How about you?
Wow. Oh no, I'm super busy. It's too much going on, too many fun things to do in life. So
I saw that we have the Egypt tour book out now.
Sure do.
Has there been any response to it yet?
Not like directly yet, but we've had a lot of orders already.
Excellent.
And I've had a lot of people on Facebook, after I posted it, just say, okay, I'm ordering that. And a couple people I was talking to on the phone, oh, I need that. So it's really kind of exciting because this is different, and we're doing something other people haven't done before, which is, here are the parameters. Here are the possible answers. These answers cannot be true, but there's a range of possibilities. Most people are like, this is the Pharaoh of the Exodus. It's like, yeah, good luck, man. You can't get it that accurate.
That is very wise. I do appreciate this approach. It has my endorsement.
Well, thanks. This is my basic approach to life. This is how I approach science. It's how I approach creation. It's how I approach theology. I want to know what I can know and what I can sink my teeth into like a bulldog and never let go. And then I want to know what's more like a marshmallow. If you try to sink your teeth into it, you bite it in half and it makes a big mess.
Mm.
And there are just some things you can't be dogmatic about. Like, what was the exact year of Noah's flood? You're not going to figure that out.
The exact year?
Yeah, it's not going to happen.
I'd be happy if I had the century.
Exactly. There's so much variability in some of these numbers. You can't exactly know. And even in theology, I'm writing an article with Lita Kozner about, actually, I'm writing the article, and I'm going to ask her to be my co-author because she's already written on it, but it's about the differences in the genealogies of Jesus in Luke and Matthew. They're totally different. They're not the same source material. They're radically different. Totally different sets of names, and yet they're both supposedly genealogies of Jesus' father Joseph. And I think there's a third explanation that no one at CMI has ever talked about. And so I'm writing this, but I'm being real careful, trying to not be dogmatic, because when there's gray, you can't say this is the answer.
Or turn the whole article into a great big disclaimer. It's like, let's go down Disclaimer Avenue here in Disclaimerville and talk about the disclaimer for 900 words before we get to the article, which is about 300 words.
Yeah, that's always hard. That's hard to write like that. Sometimes you do have to. But here, you want to hear the gist of it? It's really cool.
Yes, please.
Matthew might not be a genealogy.
Oh, interesting.
Matthew might be a king list.
I was just reading that yesterday.
Oh, what?
Anyway, go ahead.
What? Someone's got my idea.
Seriously. I'm just starting to go through the New Testament.
If you listed out all the kings and queens of England, it's not a genealogy because different families ruled England at different times. But in Matthew, since we don't have the source material, all we have is the list of names.
Okay, yeah.
And it gets very interesting from that point on. Anyway, we'll have to save that for a future episode if you want to talk about it.
Okay, I get it. If you're still working on the idea, if you're still workshopping that idea and you want to follow it up, that'd be great.
Okay.
I am really excited. I just made a couple of upgrades to my desk and I'm getting a new computer. So this time next week, we may be recording Equinox on a much more state-of-the-art Mac computer. And I'm sure it's going to change everything. Our podcast is going to be in 4D.
Really?
We're going to be able to sell tickets. It's going to be great. No, actually, I think it's going to sound the same, but I'm really looking forward to it. That's the news in my world. I'm just dying for that computer to show up in the mail.
Cool.
So I'm ready to get on to the show.
Yeah, me too.
We were talking about explosives and weapons and ballistics, and it got so good, we didn't have enough time to continue, and we need to pick up where we left off. Last time, you were talking about you talked about the history behind how they discovered explosive powders, how that became gunpowder, how that became black powder, where TNT came from. You explained how Nobel created the stable version of nitroglycerin. You went on to the bigger bombs and incredible Civil War history anecdotes. And you talked about the Kennedy family. It was a really good episode. But there were a couple of things we didn't get around to. For example, we wanted to talk about torpedoes, but we got to save that for another episode because there's still more to talk about. Bombs.
Yep.
I think you're ready to talk about bombs. And remember, this all began when we were thinking about the explosion in Beirut.
Yeah.
I think it's appropriate we continue to pick up with bombs first before we get around to the torpedoes.
Yep. We'll have to skip torpedoes for now. But let's jump to the atom bomb. The next obvious bomb candidate after TNT, nitroglycerin, is the atom bomb. But in trying to figure out how to explain how an atom bomb works, I realized, like so many other episodes we've done, we've got to jump into some of the history. And the history is fascinating specifically because they discovered all these things required to make an atom bomb right before they built the atom bomb.
Huh. So what do you mean they were planning to make one and then they made these discoveries that made it possible?
No, they had no idea.
Oh.
I mean, we blew up the first atom bomb in 1945. We didn't even know that an atom had a nucleus until 1911.
Wow.
We didn't even know about neutrons until 1932.
Well, I didn't know about them until episodes, what were they, 20 and 21 of Equinox, which we talked about the atom. Yeah.
All right. So before we get to blowing things up with a bomb, we have to talk about the discovery of radioactivity. Now, there's several different forms of radioactivity. There's alpha particles, beta particles, and gamma rays. And people didn't realize how these things were related for a long time or what they were. And one thing at a time. The first thing that was discovered were X-rays. Just a powerful light beam, like a gamma rays, a powerful light beam. And that was discovered in 1896 by Wilhelm Röntgen. And Röntgen is a unit of measurement now. So if you go to your dentist and you get so many X-rays, they measure the exposure in Röntgens.
Huh.
And what he had a cathode ray tube, which is what drove the old-fashioned televisions that we all grew up with. Half the people listening to this would not have ever grown up with one of those.
Right.
But oh man, like watching the first season of Doctor Who, the new BBC Doctor Who series.
Yeah.
They had flip phones and fat TV monitors.
Nice.
I'm shocked. That was like yesterday for me.
Were they doing it for style? For like a period of the...
No, that was the technology when the first season of Doctor Who was out.
Oh, okay.
They didn't have the flat screen, thin monitors like everyone has today.
Right.
We had laptops probably, but it's not like, you didn't hang this giant TV on your wall. You had to have a fat TV and flip phones. They didn't have smartphones yet. That was like yesterday. But anyway, the cathode ray tube, which is later on, they'd point one at your head on a phosphorescent screen. That's where the TV came from. But they realized that there was something coming out of that they named an X-ray. And then that same year, a guy named Becquerel, he thought that uranium, because it sometimes glows in the dark very faintly, he said, he bet that if you expose it to sunlight, it would be phosphorescent. It would glow in the dark if you expose it to sunlight. Like, phosphorescent paints and T-shirts and things like that. I have one had a picture of the Milky Way. If you turned off the lights, you could still see the Milky Way. It would glow in the dark because it would absorb sunlight or regular light. So what he was doing, Becquerel was taking photographic plates that didn't have film yet, but had photographic plates, and he would put uranium on, expose it to sunlight, and then it would expose a photographic plate. Cool. But then he left one in the drawer, and he pulled it out of the drawer. He says, this has never seen sunlight. I'm going to expose it. And he noticed that the uranium had exposed it in the dark.
Oh.
And he said, what is this? There's no light here. There must be some invisible rays coming out of the uranium. And we're going to call this radioactivity in a couple of years.
Oh.
But this is a mystery. And this is 1896. 49 years later, we're going to blow up a city. I mean, what's 47 years ago? 1970 something. That was not long ago. And it would be like in 1970 we didn't even have a computer, and today we have a smartphone. That's about how fast things changed back then. Then 2 years later, Marie and Pierre Curie, they discover radium, an element that glows in the dark all by itself, and polonium, named after Poland, and thorium, named after Thor.
Awesome.
It was from Norway. So they discovered these 3 brand new elements, and they were able to put them on the periodic table of elements. Neat. And they won a Nobel Prize for that. And then Marie later on won another Nobel Prize for the extraction of these things. So it's like the process of getting these things out of uranium ore. She got a second Nobel Prize for that. What an amazing family. Did we talk about the movie Radioactive?
No, we didn't.
We didn't. Okay, brand new.
I don't remember.
Oh man. Okay, I'm gonna Google here. Because I don't remember if it was Netflix or Amazon. It's on Amazon. It's called Radioactive. It is the story of Marie Curie, and it is an amazing movie. Except there's a little bit of nudity in it, and it's like the shortest, briefest nude scene in the history of cinematography, and it didn't even need to be there. But they had to flash Rosamund Pike jumping in a lake. I was very upset. But you also get to know that Marie Curie wasn't a very nice person, and she did have an adulterous affair after her husband died with a married man. Ouch. Anyway, and didn't really seem, and at least in the movie, they really played it up like she didn't care. So not a good person, but an amazing woman, and the whole story of her life is fascinating. I've read some biographies and other places where she's mentioned. Just
Yeah.
an amazing person. And they could have, her and her husband, before her husband died, could have gotten other Nobel Prizes, but they missed it multiple times in their life. Like, oh, that was the answer. So they're doing this experiment and not figuring it out, and someone in England figures it out, someone in Germany figures it out. So I could not imagine being in a field of science where, I mean, Nobel Prizes are just dropping out of the trees because they're learning things that are, low-hanging fruit, but they didn't have any technology to actually do what they needed to do. And it was happening so fast. Today, our science is advancing very quickly, but not monumentally.
Right.
It's advancing quickly and incrementally and faster than ever before.
That's a good way to describe it.
But, I mean, when you discover, radioactivity, I mean, that's huge. When you say, oh, if I, put a little bit of lithium tetroxide in this boron thing, I can make a photovoltaic panel that's 1% more efficient than anyone else has ever done before. Ha ha ha.
Yeah.
Well, that's $1 million decision right there, but it's not the same sort of thing.
Wow.
So Henry Becquerel, 1896, discovers that uranium can expose film. Marie and Pierre Curie discover radium, polonium, thorium. They suggest that maybe this is something called radioactivity. 1902, Rutherford, who we have spoken of before. He ran the Cavendish lab, and we've spoken of the Cavendish lab and Cavendish before too. But these two guys, Rutherford and Soddy, they claim something impossible, something that in the medieval times, people talking about transmutation. They're trying to turn lead to gold or straw into gold. They're trying to make everything into gold, and the alchemists could never figure out how to do it. But they claim alchemy. They claim that radioactivity is a spontaneous transmutation of one element into another.
And were they right?
Yes, but that was such a radical departure from the last several decades of science.
Wow.
People actually resisted it. They did not like this. But this is 1902. They didn't even know the shape of an atom yet. They didn't know what was inside matter.
Wow.
They had these things called elements. Okay. They didn't, it wasn't until 9 years later where Rutherford discovers the nucleus.
It feels like they discovered some of these things out of order.
Yes, very much so. In 1919, 8 years after that, Rutherford discovers the proton. What is this guy Rutherford? He discovers radioactivity, discovers a nucleus, discovers a proton. This is unbelievable. This one guy, over the course of 20 years, literally built our modern understanding of atomic science.
Wow.
Now, everyone else is helping. There's lots of other people experimenting. But he did several critical things that we would be nowhere without these discoveries. 11 years later, 1930. We're getting awfully close to 1945. 1930. Botha and Becker, right? German. So all these people are English, French, and German so far. They are shooting alpha particles, which are helium atoms, at beryllium. And coming out of the beryllium are high energy particles. They don't know what they are. Marie Curie's daughter and her husband, they got it wrong. They said that these are just protons. But other people said, yeah, but if you send these protons past a magnetic field, they don't bend. Charged particles running through a magnetic field will curve. These things don't curve. So 1932, James Chadwick announces a discovery of the neutron. And the neutron is what is required. Understanding of the neutron is what is required to blow up an atomic weapon. But this is 1932. 13 years later, Hiroshima is evaporated by our understanding of what neutrons do.
How long before that bomb had they figured it out and just were biding their time before they used it?
6 years.
Wow.
We're not quite there. They can't. Okay, we have a neutron. We have radioactivity. Okay, great. We don't have nuclear bombs yet. They're not. There's a couple more things that are needed before you say, "Hey, I think we can blow up half the world." No, it doesn't work like that.
Yeah.
But what happened was once they discovered neutrons, they're like, "Well, this is a heavy element, a heavy particle. It's the same exact mass as a proton, but it's not charged. So we can shoot it at a nucleus, and it's not going to curve away. There won't be any, protons reacting with protons." And they start bombarding a whole bunch of different elements with neutrons just to see what would happen. And guess what happened when they did that to uranium?
I'm going to assume it exploded.
It did not explode.
Oh, it got hot?
It got really hot. It released a lot of energy, and they started looking at the particles coming out and said, "Wait a minute, there's more neutrons coming out than the neutrons we're shooting in." This is 1934. We're now 11 years away from the A-bomb. But Fermi didn't understand what was happening. It wasn't until 1938. Two Germans, Meitner and Frisch. One of them was Jewish, and it was her, and she had to flee to the Scandinavian countries. I think she was in Sweden. She ended up in the Nobel lab and associated with that type of things. And she was working with some people back in Germany still. And she and her co-author announced that when you bombard uranium with neutrons, it splits. Oh. And they said, well, here is the atomic mass of uranium. Here's the atomic mass of the products. There's a little bit of a difference. Oh, that's the energy that's released, because Einstein told us that E equals mc squared. You can convert matter into energy. And they said, wow, this is a lot of energy.
Yeah.
So this is leading right up to World War II. And this is German scientists that are figuring this out. And in 1939, before the U.S. got into World War II, Albert Einstein writes the U.S. president pleading for the U.S. to make a nuclear bomb.
Oh, wow.
Because Einstein was German, right? And he knew the Germans were working on nuclear weapons. What he didn't know was that they never would have gotten there. They were so far behind. They were doing ridiculously slow. It took America. It took billions of dollars being thrown out of the problem. It took radical departures from everything ever done before. It took an entire military industrial complex that Eisenhower talked about, the next decade. It took this massive manpower, money, and industry to produce a nuclear weapon. And Germany just wasn't there. They weren't thinking that way. Germany was amazing in their technology and super good in engineering. And they invented a lot of amazing things like the jet plane and, the V-bombs and all sorts of crazy cool stuff. But they were never able to build big like the Americans could. Just when we turned on, there were so many of us in such a vast country with so much resources, we could just build and build and build and build and build and build like no one else could do it.
Well, I see. Yeah.
And we had so much manpower that they can throw, 1,000 people at this and 1,000 people at this and another 1,000 people at something else and figure out all these problems. And they figured them out one at a time. Ding, 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 ding. And during World War II, we invented the weapon from hell because we thought the Germans were, but they weren't, and we didn't know it. If the Germans hadn't been pursuing this, we probably never would have done it. Why waste millions upon millions of dollars?
Right.
If it wasn't a threat.
Right.
It would be a theory. Hey, if we do this, we could probably blow up half a city. Hey, but no one would have ever done it. It would have cost too much money. Plus, we're going towards nuclear power, not nuclear bombs. And nuclear power is a whole lot easier. Cool, huh?
Yeah, very.
All right. So, how do you build a bomb?
I have seen several examples where they had one open and they were putting the finishing touches on it in a movie.
Yep.
And one thing that has struck me as odd is how solid parts of it are, how much of it looks just like technology because it's computerized, or how many parts of it look like they're hollow and incomplete. I would have thought the materials would have been a little bit more streamlined.
Yeah.
I don't know if density is a good idea. Like these days, if you pick up a tablet computer, they don't have a lot of air gaps inside of them. So they feel very solid and kind of weighty for their size. Mm-hmm. But then if you picked up an older tablet or ones made of plastics with some more air pockets in them, they feel lighter for their size comparatively.
For their size. Yeah.
And I kind of wonder about bombs. Like a lot of this stuff has to be engineered. It's not just about finding the right chemicals to make it explode easily.
Oh no. Yeah. Yeah. The engineering that goes to get the thing to explode, you need a lot of things, a lot of parts. And people have to think through a lot of problems. And if any one of those things didn't work, we would have dropped a dud on Japan and they would have figured out nuclear weapons when they took it apart. It was risky. Super risky. And those bombs, we're talking 10,000 pounds to drop a few pounds of uranium. The trigger, the atmospheric, the density sensors, so they know what altitude they're at, the timers, the actual bomb. You need a bomb to blow up a bomb. You literally have to blow something up to blow up uranium or plutonium.
Oh, that makes sense. I hadn't thought of that, but that totally makes sense.
See, the deal is, you need a critical mass. It's called a critical mass. You need so much uranium in a certain area that when a neutron comes out of one fizzing or fissile or one uranium atom that's breaking apart, it has a really good chance of hitting another one, which might produce more than one neutron coming out. And you have to have a lot of uranium in one place. If you bring it together slowly, it'll start fizzing. It won't blow up. And the atoms will start disintegrating at the contact point, but it won't go critical. So what they do is they take the first bomb had more than one critical mass of uranium. In fact, I think one side of it was more than one critical mass, but it wasn't a sphere. It was in a funny shape, like a half a hemisphere, and I think it had a hole in it or something like that. So it was actually more than one critical mass, but it wasn't in one solid little ball. And what they did was they took another piece of uranium and put it in front of a bomb. And when the bomb blew up, it drove the little piece of uranium into the big piece of uranium like a bullet.
Nice.
Therefore, almost instantaneously bringing enough uranium together that it went critical all at once and blew up. That was the little boy bomb that we dropped on Hiroshima, 6th of August, 1945.
Something else that strikes me as odd about these bombs is that they are engineered around taking down a target.
Yeah.
Because if I understand atom bombs, they're sort of like you've got the simple levels of explosives for fireworks. Then you have more precision applied for something like a bullet, but it's not a lot. But then you go one step further, maybe for a grenade, and you need something that could potentially kill a person or two within a certain small radius of maybe a room.
Okay. Yeah, proximity weapons. Yeah.
From the next level up, you have to have some kind of shoulder missile launcher, maybe a bazooka like cannon, a rocket launcher.
Yeah.
And you go up and up until you have those larger bombs. You see that they drop from the larger aircraft, jets and the like. But there is sort of like a huge just difference in scale between those bombs that could take out a 4-story building, and then the next thing up, which is it's going to obliterate an entire city.
Yeah.
It seems like there's a huge gap there.
Well, this is why they invented the backpack nuke.
The backpack nuke.
The small nuclear weapons, the low yield nuclear weapons that could be used to take out, a small town or the size of Beirut.
Okay.
The Beirut explosion, like 2 kilotons or something like that, I think was the yield. It was about the size of what we would call a backpack nuke.
Would they be considered more modern than the A-bomb itself?
Oh, yeah.
Okay.
Oh, yeah. Much, much more modern. In fact, they'd be much more efficient at creating energy.
That makes more sense.
The first, the little boy, I think it was 64 kilograms of uranium, but only about 1 kilogram actually reacted. So they spread 63 kilograms of uranium, got blown around the city, and about 1 kilogram of it blew the city up.
Unbelievable.
Part of the radiation dosage, I guess. Well, I guess if you take 64 kilograms and spread it across something the size of a city, I don't know what radiation load that would be. I think it'd be pretty bad, but I don't know. Either that or they found the core afterwards. That might be true too. I'm not exactly certain. I know the U.S. swept in there. In fact, my uncle Ernie, he said he was one of the first U.S. soldiers stationed in Japan at the end of World War II in Hiroshima. So he said he had crossed the Pacific in a flat-bottom boat. I'm not sure exactly what that was, but that's what he said. And that, of course, he was gearing up for the invasion of Japan, which everyone said is going to cost about 1 million casualties.
Wow.
And he was happy that they had dropped the A-bomb because we knew, from the Okinawa. In fact, I just started reading a book about the Okinawa invasion, the casualties and the tenacious fighting of the Japanese. It was carnal. It was awful.
Right.
And said, when we invade the home island, the big islands, it's going to be even worse. And so after the war was over, they stationed him in Hiroshima. Now he died a couple years ago, and I didn't see him very often because he lived way up at state New York on the Canadian border on a lake. And I really hadn't seen them since I was a kid. They started vacationing in Florida when my parents had moved to Florida. And so every once in a blue moon, once every couple of years, we'd see them for an afternoon. But I never really had a chance to sit down with them and really quiz them about World War II. And I missed the opportunity because he died a couple of years ago. But that just would have been a fascinating conversation. Just missed on my part.
Yeah.
Anyway, back to the story. In order to blow up a bomb, you need uranium. Problem is, the most common type of uranium, like 98%, is uranium-238, and that doesn't blow up.
Why not? That sounds counterproductive.
Yeah, it is. You need uranium-235, which is like 0.7%. If you have a lump of uranium, less than 1% of it is a type of uranium you want.
Oh.
But uranium-235 and uranium-238 are the same element. They react with the same things. How do you separate two things like that? It's if you want to separate iron and carbon, that would be easy. Even iron and nickel you could probably do. You just got to react it with something that reacts with one of the things and not the other thing. But uranium is uranium.
Yeah.
And so what the US government started doing was making uranium hexafluoride. This doesn't sound so smart because fluorine is toxic. Fluorine destroys any organic molecule it touches. And uranium is radioactive. This is like the most toxic thing you could imagine, and it's a gas.
Ugh.
This is a really dumb gas to make, but the nuclear industry, even today, they'll take uranium ore and expose it to fluorine. Oh, come on. And make uranium hexafluoride. And I think the US government used 4 different methods of separating them, but the one that I'm most familiar with, and I think they were doing this at Oak Ridge, they had it's Oak Ridge National Labs in Tennessee. They had a tunnel that was like 5 miles long. I don't know if it was a straight tunnel or if it went around corners or not. I just know it was 5 miles long. And they take this uranium hexafluoride gas and put it at one end of the tunnel, and then go to the other end of the tunnel. And as that gas diffused through the tunnel, because uranium-235 is less than 1% lighter, right? That number is the atomic mass. 235 versus 238. 1% of 100, that's what's 235, 238, that's 3 out of 200 something. So it's about 1% difference. But if you diffuse this thing across 5 miles and go to the end, the first atoms to get to the other end are all uranium-235. And you just start sucking all the gas out of the tunnel. And then when 238 starts showing off, you stop. And you do it again, you do it again, you do it again. And you get what's called enriched uranium and depleted uranium. It's depleted in uranium-235. It's worthless for nuclear reactors. It's worthless for nuclear bombs. But you can make a bullet out of it and put it in an A-10 Warthog and destroy tanks or hardened bunkers or anything, because uranium is such a heavy element. We make shells out of it and shoot it at things. That's where the depleted uranium comes from. It's from this process. It's the leftover uranium that's not good for anything except shooting at things. Anyway, so now we have enriched uranium. That's one way to do it. Another way to do it, and you remember back in the Gulf War when everyone was worried that Iraq had a whole bunch of things they called centrifuges, and the number of centrifuges.
Yeah, I heard of centrifuges, but I didn't really know what they were.
Okay, well now Iran's got centrifuges. We're all worried about there. What it is it's a thing that spins really fast. In fact, it spins so fast, it spins at like 1 million G. It's like 1 million times the force of gravity. And it's just a long tube that spins really fast. And if you put uranium hexafluoride in that tube, the U-238 is heavier. It will be slung to the outside. The uranium-235 is lighter, 1%, and it will collect in the middle. And then you can siphon off the gas in the middle and put it in another one and do it again and put it in another one and do it again and put it in another one and do it again. You have to do this for the nuclear power industry because we need our uranium. It's got to have about 4 to 6% uranium-235, or it's worthless. You can't burn it. But if you enrich it to about 4 to 6%, you can put it in a nuclear reactor and it will burn real hot, and you can boil water and run through a turbine and get electricity out of it. But for nuclear bombs, you need about 80 to 90% enrichment. It has to be mostly uranium-235 because 238 will be a poison. It'll suck up the neutrons and it won't blow up. And that's the one thing we're worried about. Like some place like Iran, they're like, oh, this is just for our peaceful nuclear power industry. Nod, nod, wink, wink.
Right.
Yeah, sure. You do that for nuclear power, but all you got to do is keep on enriching it using the same exact equipment and you have high-grade weapon uranium. And that's what we don't want other countries to be doing. Because honestly, I mean, we don't, the powers, the nuclear powers in the world, they signed the Nuclear Non-Proliferation Agreement. They don't want other countries developing nuclear weapons because it destabilizes everything.
Oh, definitely.
And we don't want a crazy country with nuclear weapons.
For sure.
Okay. So we need uranium-235. You can use a tunnel diffusion. You can use a centrifuge. There's a couple other ways you can do it. But once you have it at a really high concentration, if you get enough of it in one place, it will go critical and you get an atom bomb. Nasty, crazy, dangerous. So the little boy bomb that they dropped on Hiroshima was 2 pieces of uranium and they drove one into the other. About 1 kilogram of uranium was burned in the process and it produced 15 kilotons of TNT equivalent.
Wow.
So trinitrotoluene, which we talked about, explosive, extremely dangerous, really high, powerful explosive, will take 15,000 tons of it and detonate it all at once.
That's a lot.
It's a lot. If the Beirut explosion was 2 to 5 kilotons, imagine something 5 to 10 times larger. That was Hiroshima. I mean, that Beirut blast, that was significant. That was one of the largest explosions in world history. Especially one of the largest ones that wasn't an A-bomb. But 15 kilotons, that was the first atomic weapon. 3 days later, because the Japanese didn't surrender, we dropped the Fat Man on Nagasaki. This didn't use uranium. It used plutonium. Plutonium-239 specifically. And it didn't use the gun-type reactor where you had an explosion that drove one piece into another. It actually had a shell, a sphere of plutonium. And they blew a bomb up around it and collapsed the sphere.
Huh.
And the reason for that is the Hanford bomb-producing factory in Washington wasn't producing pure enough uranium-239. It actually had some plutonium-239. It had some plutonium-240 in it.
Okay.
Which burns too fast. And so as you're driving it together, it would start fizzing, and it would ruin the whole reaction. And so they couldn't use the gun type. They had to literally invent a sphere that could be blown up in all directions simultaneously to collapse it. And you had to make it like, if you just had a lump of plutonium, it would be, this size. They actually had to make something about double the density. They had to squish the metal into itself to get enough plutonium-239 together that it would blow up. That one had 1/10 the amount of plutonium as the uranium in the little boy bomb. 1/10. And had about 1 kilogram. So 1 kilogram and about 6 kilograms. So the efficiency was much better. And it was 21 kilotons. So 1.5 times bigger. And we dropped that on Nagasaki. Now, Nagasaki was a major industrial area. There wasn't as many people that died, even though it was a bigger bomb, because Nagasaki was in a valley. Hiroshima was a flat city and had maximum damage. But Nagasaki was in a valley, and we dropped it in an industrial area, and that blew up, and the residential area didn't get hit as bad. Now, radiation, of course, killed lots of people over time and things like that. But the sad thing is, Hiroshima and Nagasaki were 2 of the centers of Japanese Christianity.
Oh.
But it was war.
Yeah.
And we had to drop the bomb on these cities. But Nagasaki was the secondary target. It was cloudy over the primary target. So they picked city number 2. Shut down the Mitsubishi plants, killed a lot of people. In Japan, said, we give up. 21,000 tons of TNT. And they don't explode it on the ground. They explode it in the air. Because an airburst maximizes the spread of the blast wave. It reaches.
Oh, that makes sense.
It reaches further than if you blow it up on the ground. So if that Beirut explosion happened, if it was like a industrial, like in that grain elevator, if they were storing all that stuff on top of the grain elevator, it would have blown up a lot more of the city than it did because it blew up on the ground. Yuck. Okay, so that is A-bombs.
The A-bomb.
But that's not how bad a bomb gets. We don't use A-bombs anymore.
That sounds very frightening.
In 1951, just 6 years later, we blew up the first thermonuclear weapon. It's not an atomic bomb.
So when people say thermonuclear, they don't mean a A-bomb. They're talking bigger.
Well, it has an A-bomb on it, but they use the A-bomb to start the next reaction.
Oh, wow.
Just like we need a bomb to start an A-bomb. You need a conventional weapon to start an A-bomb. Well, this one used a conventional weapon to start an A-bomb that then squishes hydrogen, deuterium, and tritium. Those are isotopes of hydrogen with extra neutrons. It fuses them together like in the core of the sun. And that fusion reaction produces an awful lot of heat, and it releases a lot more energy than an A-bomb. We don't measure thermonuclear weapons in kilotons. We measure them in megatons.
Oh, wow.
Millions of tons, not millions of pounds, millions of tons of TNT equivalent. Hiroshima was nothing. It was a pebble dropped in a pond compared to a thermonuclear weapon. But only, 1951. This is, let's see, we discovered radioactivity, it's first described in 1902. We discovered the neutron in 1932. 19 years later, we're using fusion reaction weapons and measuring them in megatons. The largest bomb ever detonated was a Russian bomb they called the Tsar Bomba. The Tsar Bomb. It was 50 million tons of TNT equivalent. 50 megatons. That is shocking. I mean, what could you even do with a weapon like that? It's actually useless. Because first of all, it causes too much radiation, causes too much damage. And a bunch of little ones would be much better than one big one. Plus, if you're trying to get one big one through, you had a high likelihood your plane's going to get shot down or something like that. Or it might fail to detonate. So instead of going that route, the U.S. went the many missile route. And very soon we're inventing intercontinental ballistic missiles. And we are inventing missiles with multiple warheads. So they actually carry multiple thermonuclear bombs per missile. And then we figure out how to target multiple targets with one missile. That was a trick. That took a lot of figuring out, a lot of calculating. But now one missile can go up and it can drop bombs that go in different directions and blow up different. I don't know how far apart they can be. Maybe 100 miles, 50 miles. I don't know what it is. But they can spread the bombs around. And so you're talking, one missile might be 1,000,000 times the force of Hiroshima. And the American government built thousands of these.
Wow.
And the Russian government built thousands of these. And China built who knows how many. And France and Britain built some also, and apparently Israel. Interesting. And we went through now, some of our listeners don't remember the Cold War. I grew up in the tail end of the Cold War. So we didn't have bomb shelters like in the 50s and 60s. And, I was growing up under Ronald Reagan. Everyone's like, go Reagan,
Yeah.
And, we're going to get the commies. And we weren't
Star Wars.
Yeah, Star Wars. We weren't scared. We were winning. And I remember when the Berlin Wall came down. That was unbelievable. In fact, I went to Berlin just 2 years later. And I went to Eastern Europe, Poland and Lithuania, Latvia, Estonia, and Russia 2 years after the wall came down, just to see. And it was horrible. People were dirt poor. I mean, no toilet paper. No electricity half the time. No food in the restaurants. It was awful. But I had to see it. But we went through a period called mutually assured destruction, which the acronym is MAD. And it was literally, if you launch a weapon at us, we're going to blow you up and you will have nothing. We will drop 10,000 nuclear bombs on every single part of Russia and you will cease to exist. And the Russians said the same thing, but even though they're communists, the Russians are more practical. Americans are cowboys. You come at me, I'm coming back at you with all guns blazing sort of thing. And we spooked them. And they believed us that we would literally blow them to kingdom come. And you know what? I think we would have. That was the plan. If there's a nuclear war, nobody wins, everybody dies. And probably for that reason, now some of you military historians might be jumping on my case here, but probably for that reason, we did not have a nuclear war. Although Eisenhower wanted to drop nukes on China during Korean War, he wanted to blow up parts of China during the war, and that would have changed history right there.
Yeah.
Because the only time nukes have been used in combat was twice. It was in 1945, and everyone in the world said, whoa, this is crazy. This has gone too far. And that's one of the reasons why we've had all these wars in Afghanistan and Iraq and another Afghanistan. It's the U.S. and the Soviet Union were fighting proxy wars. We were fighting the Russians in Afghanistan. We were. When they invaded Afghanistan, we were supplying the Afghanis with weapons to fight the Russians. But we weren't there. one reason was impractical to be there. George Bush changed that, but it was a dumb idea to try to invade Afghanistan. The Russians figured that out. But also, we didn't want to antagonize them to the point where we would start throwing nuclear weapons at each other, which is why the Cuban Missile Crisis was such a huge bad thing. I mean, under Kennedy's administration, early 60s, our satellites, after we invented satellites, we're shining them down on Cuba, and like, wait a minute, they're building nuclear missile installations, 70 miles away from Florida. And this was, well, then again, we had nuclear weapons on the border of the Soviet Union. I mean, we had surrounded them with our army bases and friendly countries and NATO and stuff like that. So, they were doing what we were doing, but, well, we called their bluff and they pulled their missiles out. And history gets really interesting at this point because now mankind has the ability to destroy itself.
Yeah, to ruin the entire planet.
And ruin the planet at the same time. However, I know it's not going to happen because I know in the Bible, Jesus is going to return, and when he returns, there will be people alive on this earth. Now, it doesn't say it'll be a technologically superior earth, but we're not going to go through some nuclear holocaust where everyone on Earth dies except for a few scientists on the Antarctic Research Station. That's not going to happen.
Right. Yeah.
It's unallowed.
Doesn't add up. Interesting stuff. One thing I was wondering about all the ballistics. Are they called ballistics, or are ballistics something more niche, like gunpowder used in bullet shells?
Yeah, ballistics is things flying through the air. Now, we have nuclear ballistics. They have invented a nuclear bomb you could put in a cannon and shoot it in a shell. But that's tricky because you're talking about a huge amount of acceleration for a very complicated machine.
Yeah. I'm even picturing like you fire it from a cannon and it doesn't go far enough that it doesn't blow you up.
And that's the other problem, yeah. And plus, yeah, even no matter how far you shoot it, you can never be far enough away from a nuclear explosion. But those are the tactical nuclear weapons, the low yield, blow up half a city sort of things. But even so, that's just dumb.
Okay.
It's just not. It's like we need to pursue the technology and figure out how to do it, but you don't ever want to use such a thing.
Oh no.
No.
Well, I think that's good. You want to wrap up there?
Yeah, I think we should. I don't
Good.
want to be any more depressed.
No, I'm not depressed. I found it very fascinating. But I probably will go watch something funny and silly now with my wife and eat some popcorn.
Yeah, best fails of 1998 or something like that. Yeah.
Right. Maybe that video about squirrels by Mark Rober on YouTube again. All right.
Brilliant.
So, well, thanks so much, everyone, for joining us.
Oh, no. Joe, wait. No. Back up. There's something I forgot to talk about.
Okay, pause.
Okay.
Cut, everyone.
No, this is something.
Back to your places. Yeah, Rob, go ahead.
There's in the notes, and it just the way we talked about it, the conversation evolved in a way I didn't expect. But
okay.
There is a place in Africa, in Gabon, West Africa, where there's a uranium mine. And as they're mining this uranium, they notice that they find these pockets that have hardly any uranium-235 in it. Everywhere in the world, including the rest of this mine, uranium-235 is like 0.7%. But to get to these pockets, they're like, there's no uranium-235 here. And what they have determined is that these uranium deposits went critical. And the U-235 burned fast, like in a nuclear reactor burning.
Whoa.
And it ate up all the uranium-235 in that section of the mine. It's a natural nuclear reactor.
Wow. Unbelievable.
Now, it wasn't at 80 or 90%, which is good because then it would have blown up. But I don't think you could ever get it there. It would have been fizzing away as it was accumulating. But these rocks, there's the Oklo National Reactor. It's a Precambrian formation in West Africa. In fact, we have an article on it on creation.com. It's just totally cool that this actually could happen in nature, and scary thinking. Because, I mean, what if just by dumb luck, in some evolutionary world, there's nothing preventing a lot of uranium from being on a planet? That would be really bad, because then the planet could blow up. Can you imagine if we're sitting here having a cup of tea and we figured all these lovely ways of solving environmental issues, and humans are just trucking along just fine. All of a sudden, all the uranium in the core goes critical. Whoops.
Oh, wow. My word, that definitely puts an interesting perspective on everything.
But there's very little uranium beneath the crust. The core of the Earth isn't radioactive. The mantle isn't radioactive. A little bit, but not. The crust is where almost all the radioactive material is.
That makes sense. Huh.
Anyway, I need to throw in the Oklo natural reactor. Sorry, everybody, for interrupting the stream of consciousness. We can now get to the end credits. Roll the credits.
Right, of course. If you want to dig deeper into any of these topics, you can find links to stuff we discussed in the show notes or on our website. They're available at nightowl.fm/equinox/25. And those show notes can also be found in the podcast player right along with this episode in the app on your phone. You should also check out Biblical Genetics, where Rob is, that is his other project. Biblical Genetics is also available on Facebook and YouTube, where you can watch the videos and join the discussions in the comments. If you want to find me, I am at JCS Darnell on Twitter. Until next time, goodbye, Rob.
Goodbye, Joe.
You have been listening to Equinox.